Hi, today we're going to talk about how do you measure the accuracy of multi-label classification problems, an amateur's approach. So what is a multi-label classification problem? I'm pretty sure you know what this is when you click the video, but it's basically when multiple things are the answer to our problem. So for example, you have some input given to a model, and the model predicts multiple outputs. And from these multiple outputs, you could have two values that are correct. So our model is basically giving multiple labels the correct value. Measuring accuracy. Looking at the accuracy for a single example, we have to calculate the precision and recall for each example. So if we have 100 examples, we have to calculate 100 precision values and 100 recall values. To get the precision value, we calculate the intersection of our true labels with predicted labels. So these are the labels that our model predicted to be correct, which are actually correct, divided by the total number of predicted labels. And to get the recall, we actually do the same thing. We get the intersection between the true labels and the positive labels. So this is the labels that our model got correct, which are actually correct, and divide that by the total number of true labels for our example. Let's look at an example. So here we have the input, which is just a string. This is from Stack Overflow. Somebody asked a question: how do multiple time dimensions appear to allow the breaking or reordering of cause and effect in the flow of any one dimension of time? I have no idea what the answer to this question is, but I just got it from Stack Overflow, so let's go with it. We give this to our model, and our model actually predicts metaphysics, time, and health to be the predicted values. So we can actually see that the total number of predicted values is 3 here. And let's say that we get metaphysics correct, time correct, but physics was incorrectly classified, so we got physics wrong, and the rest are incorrect. So this is actually the set of total true values, which is also 3. Because physics is correct, time is correct, and metaphysics is correct, but we only got 2 out of those 3 correct. So the intersection between the true labels and the predicted labels, which are correct, is equal to 2, since we got 2 values that were predicted correct, which are actually correct. So now to get the precision, we take the intersection between the true labels and the predicted labels, which gives us a value of 2/3. Similarly, to get the recall, we take the intersection between the true labels and positive labels and divide that by the total number of true labels, which also gives us 2/3. Now to get the true accuracy, we can just average the precision values and the recall values and then calculate the F1 score, which is just a type of harmonic mean, which is kind of like this balance over here between these two variables or these two metrics. Let us imagine that we have a problem where we only have 2 examples. So let's say n is equal to 2. And let's say that for the first example, we get a precision of 2/3 and a recall of 2/3. This is n equals 1. And for n equals 2, we get a precision of 1/2, and we get a recall of, let's say, 1 over 3. To get the precision value, we get the equation 1 over n times the sum of the true positives divided by the predicted labels, and basically which is 7 over 12. Similarly, to get the recall, we do 1 over n times the sum of the true positives divided by the true labels equals 1/2. So now that we got the recall value of 1/2 and the precision value, I forgot how to spell precision, of 7 over 12, we can then get the harmonic mean of them, which is the f1 squared, which is 2 times 1 over 2 times 7 over 12 divided by 7 over 12 plus 1 over 2, which is roughly 53%.